over what we have covered so far for vectors, okay, so that we can do a recap. Okay, so we have already learned for representation, right? This same diagram is in the SLS itself. Okay, so in representation, we know how to represent it in terms of a line segment, how we write it in terms of its notation, as well as how do we write it in a column vector form as well. Okay, then we have also learned various terminologies, okay, and we need to be familiar with them. Okay, so the very first one is about equal vectors, whereby for equal vectors, just like the word suggests, equal means that everything has to be equal, so same magnitude, same direction. Okay, and in the diagram over there, we see that vectors A and B are the ones that are equal. Then we also need to know what are negative vectors. Negative vectors are things that are opposite in direction, and we know that opposite direction doesn't mean different direction. Okay, because opposite will have to be in the same path in two different ends of direction, whereby different direction can be one going forward, the other one going backwards. Okay. Then for parallel vectors, which is something that I placed in SLS, whereby we learned that for parallel vectors, so long as the line segment itself falls, okay, in the same understanding of what we understand about parallel lines, okay, they would then be parallel vectors. So the direction need not be the same, okay, neither will the magnitude need to be the same as well. So from this diagram, we see that A, B, C, E are the ones that are parallel. And when it comes to parallel vectors, okay, they are scalar multiples of each other, okay, whereby we get A equals to KE in this case. Right, I'll do more examples about parallel vectors in a moment. Okay. Then, why is it I can't get all of this? Okay. Then regarding zero vector, which is something that I have yet to cover, okay. So zero vector, like the word suggests, right? Zero, okay, it means that the magnitude itself is zero, okay, and it has no direction. We need to differentiate between the scalar zero and the vector zero. So when we are referring to a vector zero, we will write it in this manner, whereas the scalar number zero, we'll just write it as a number zero. Okay, so this one is a vector, okay, and then this one is a scalar. Okay, what is a scalar? A scalar is a number itself, just like any number that we already know. Okay, just a constant number. So a scalar has no direction.
There was something uncalled.
Okay. Right. In case you're wondering why is it that we want to have a zero vector, differentiate between a zero vector and a zero scalar, right? Okay, that's because we can take a zero scalar, multiply with, let's say, a vector itself, such that it gives us a 0, 0. So this is a vector, okay, and then this has to be a scalar. We cannot have a 0, 0 scalar, 0, 0 vector to multiply with another vector. So there's no such thing as vector multiplication as well, okay? Okay, so this one has no meaning. Alright? So we need to have a scalar 0 with a vector in order to give us a 0 vector. Okay? Having two vectors like that has no meaning at all. That's why we need to differentiate between a 0 scalar and a 0 vector. Okay? Then position vector, later on I'll talk more about it as well. Okay? So addition and subtraction, like I mentioned, I usually talk more about addition rather than subtraction, so long as we remember that negative vectors, okay, how it actually works, okay, because that will help us to switch our direction, right? And then for addition, okay, the magnitude A plus B is not equals to the magnitude of the separate individual additions, okay? So that is what we have covered so far. Let me go back to this. Okay, so let's talk more about our scalar multiplication regarding parallel vectors. Okay, so in this question 1, this is in your textbook, page 32. Okay, we want to state which of the following pairs of vectors are actually parallel. So we know that they are parallel if they can be scalar multiples to each other. Okay. However, okay, having scalar multiples to each other, so long as they are none of them are 0, okay, we can conclude that they are parallel already. If one of the numbers, okay, so for example, okay, we know that scalar multiplication looks something like that. Okay, if any one of this is equals to 0, then we cannot conclude that A is parallel to B. Okay. However, if they are not all 0, okay, that means A is parallel to B. Right? So we need to look for the scalar multiple in part I, okay, between 6, -9 and 2, -3. Alright, so in this case, we find that 3 times of 2, -3 gives us 6, -9. Okay, so they are scalar multiples of each other. Hence, we can conclude that they are parallel. Okay, because we see that none of them are actually zeros. Okay, whereas for part 2, right, we see that 14 is equals to -2 times -7. Okay, between the two vectors, looking at the x component. Whereas for 18 and 9, we know that 18 is equals to 2 times 9. Okay, so this scalar number over here is actually not the same. Therefore, I cannot express 14, 18 with another as a multiplication for -7 and 9. Okay, so we say that since there's no such value of k, such that 14, 18 equals to k -7, 9. The two vectors will not be parallel. Then for part 3, looking at -3, 6, and 4, -8. Okay, we know that I can multiply with a -3 over 4 to 4 in order to get -3. Okay, and then for 6, I know that I can multiply with a 6 over -8. Which also simplifies to be -3 over 4. Okay, so therefore I can say that so because the two vectors can be expressed as scalar multiples of each other, therefore the two vectors are parallel. Okay, questions? Alright, so that will be how we can show that two vectors are actually parallel to each other. Let's just do part B. Okay, it's an open question. That means there are many different answers, not limited to just 2 answers. Okay, we want to write down 2 vectors that are parallel to 4, -3, one in the same direction and the other in the opposite direction. Okay, so if it's in the opposite direction, that means that it must be negative of this 4, -3. Okay, so if I want something that same direction, the easiest one will be to give me the same vector. Okay, otherwise we could always just do a scalar multiplication of a positive number to 4, -3. Okay, such that we get a -6. That's one example. Okay, if you want to multiply by 1000 also okay. Okay, or you want to multiply by a fraction also okay. So long as it's a positive number. If I want the opposite direction, okay, that will mean that it has to be a negative vector to this 4, -3. But easy one will be just directly applied by multiply by -1. Okay, so we get -4, 3. Alternatively, we can maybe multiply by -2 in order to get -8 and 6. Okay, so these are some examples of opposite direction vectors, and this is a same direction vector. Okay, looking at question 2, it says that 4, -3 and 12p are parallel. Okay, so because they are parallel, that means that the 2 vectors are scalar multiples of each other. In other words, I can write 4, -3 as equals to k times of 12p. Okay, similar to how we do our matrices, we can say that 4 equals to 12k and -3 equals to kp. I can then find out what is the value of k, and in this case, that will be 1/3. So that I can apply over here to find that my value of p will have to be -9. Okay. So we need to always draw the link readily between parallel vectors and scalar multiplication of the vectors. Just for practice now 13, vectors addition subtraction works exactly the same way as our matrices itself. Okay, so I will not dive too deeply into it. Okay, so for example in question 1, let me just do part 2. Okay, if I want to find 3u minus 2v minus w, okay, that will just be 3 times of the vector 1, 2 minus 2 times the vector of v, and then minus away 3, -4. Okay, so looking at all the x components, I'm looking at 3 times 1 minus 2 times -2 minus 3 for my calculation in the x component. And then in the y component, we must not forget to take 3 times 2 minus away 2 times 1 minus away -4. Okay, so that will be how we do our addition and subtraction. So that I will get 4 and then also 6 plus 4, 10 minus 2, 8. Okay, we'll get 4, 8 as our answer. Okay. So the rest, I think you all can do lah, right? So because this one is matrices stuff, so that's why I'm not doing these calculations. in our textbook we have this section 5.5. Actually 5.5 nothing much, but I'll just summarize, okay, in a few words what the section 5.5 is talking about, yeah? Okay, you don't need to draw with me, alright? It's just information for you to know. Okay, that's all. So what section 5.5 is trying to say about expression of a vector in terms of two other vectors is that if you are given a vector, let's say AB, maybe it's around 1, 2, 3, 4, 5, 6, starting from here. Wait, sorry, 1, 2, 3, 4, 5, 6, okay. 1, 2, 3, 4, 5, 6. So let's say if I have a vector AB over here, and I also introduce to you two other vectors, let's say this vector V, and then also another vector U. Okay, this vector AB can be written as a combination of the smaller vectors U and V, whereby if I want to draw it, okay, there are two ways that we can go about drawing. Right? One way of drawing is that starting from A, I go upwards first. Okay, so for U will actually be every 1 square, 2 squares up. Okay, so this is one U, and then I can have another U over here, followed by another U here. Okay, then after that, I want to reach the end point of B, so I can have a V over here, and then another V over here. Okay, so what I see is that my vector AB can be expressed as 3 times of U plus 2 times of V in order to arrive from A to B itself. Okay? An alternative way of us to write, or in terms of going from start point to end point, is that instead of going for U first then B, I can go in the other direction. Why not we go for V first? So I can go in this path, okay, whereby I have 2 V's over here, right? And then after that, I can have 3 U's in order to arrive at my endpoint V. So in the alternative pathway, I see that I have 2V followed by 3 U's. And we know that these two expressions are exactly the same thing. Okay, so essentially what chapter 5.5 is trying to say is that for any vector AB, you can express it as a combination of 2 other vectors, and this combination itself is unique. That's all. Okay, that's what chapter 5.5 is trying to say. Alright, and that's my short summary. Okay. Next thing I want to talk about, which is more important, is about position vectors. Okay, so that is your 5.6 of position vectors. So first of all, okay, position vectors usually relies on the Cartesian plane. Okay, so you need to have your x-axis, y-axis to talk about position vector. Okay, so position vector talks about when we say position vector is position vector of a point P. Okay, so for example, if I have a point P and let's say 2, 5 over here, okay, the position vector is always relative to a certain reference point, and that reference point is always our origin. Okay, so the position vector of the point P in this case will be the vector 2, 5. Okay, and we express position vector with the notation OP because it is from origin to P itself. So position vector refers to somewhat taking the coordinates and then transform it into a vector. Right? So that's what position vectors is about. Okay? So then if I have another point, let's say 6, 3. Okay, then the position vector OQ will be the vector 6, 3. Now, why are position vectors so important? Because it helps us, okay, to determine what is PQ in an algebraic manner, whereby PQ, okay, knowing how we do our vector addition, it will be equals to PO plus OQ, because we know that the center must be the same, and PO is none other than negative OP, okay, and OP is 2, 5, OQ is 6, 3, and when I do my calculation, negative 2 plus 6, I will get 4, negative 5 plus 3, I will get negative 2. Okay, so I get the vector PQ in algebraic manner, which is 4, negative 2. And I can verify it, okay, looking at this diagram. So PQ is in this direction, right? And I know that 4 would mean that it is moving rightwards in the x direction, 4 units, positive. Okay, and then after that we move downwards by 2 units. Okay, so it is accurate to this diagram over here, whereby PQ is 4, negative 2. Okay, so it's not all the time we need to draw our diagrams. In fact, most of the time, our diagrams are not placed in a grid itself, right? So we need to rely on algebraic calculations like that in order to determine my PQ vector. Okay, so this vector addition will be important. Okay, any questions at this juncture? Right, then another thing, okay, that you need to know is that the vector PQ PQ itself as the movement from P to Q, and we call this movement a translation. Okay, so what are we translating? We are translating the point P translation of P to Q. That means that from the original OP itself, which is the position vector of the point P, when I apply my vector PQ, it will eventually give me OQ, whereby I move P to Q itself. Okay, and this satisfies our understanding about vector addition, whereby OP plus PQ, okay, the center being the same, it does give us OQ. Okay, so PQ is what we call a translation vector. Okay, so this is another term that you may actually encounter, right, as you read different vector questions. Right? Questions? Okay, so looking at this example, practice sound 14, in part A, it says that P is the point 8, negative 2, and Q is the point negative 1, 7. So we're given coordinates. Okay, we want to write down the position vectors of P and Q and express PQ as a column vector. Okay. So the position vector of P will refer to OP, and that is none other than translating the coordinates into a column vector. And then for OQ, it will be negative 1, 7. Right? Then similar to what we did earlier on, to find out what is PQ, we break it up into two vectors, PO plus OQ. And PO is negative of OP. And we find that PQ will be the vector negative 9, 9. Okay, then in part B, a point A is translated by the translation vector. So when we say that a point is being translated, that means that it is being moved from point A to point B. So with the point OA, I can form its position vector, which is 6, -7. And when I apply, okay, which means to add the vector AB, I will achieve the vector OB. Okay, and OB in this case will be 6, -7 plus -4, 5. So that we get 2, -2. Okay, but this is the position vector. The question wants us to find the coordinates of B. So the coordinates of B needs to be written clearly in coordinate form, so 2, -2. So we have covered from 5.1 all the way to 5.6. All those are all meant for us to fill out our basics and know the different terms, okay, in order to tackle our main part of questions, which is found in 5.7, okay, on application of vectors itself. Alright, looking at the time now, I will not do practice now 15, okay, now I want to do practice now 16 instead, okay. So your very typical vectors question usually looks somewhat like this. Okay. So in this particular question, it says that DABC is a parallelogram. So we need to take note of, okay, terms like this, because parallelogram has an implication whereby it means that the vectors are equal, okay, for AD and BC, as well as AB and DC, they are equal vectors. Okay. Then the question has mentioned that AB is 8A and AD is 4B. Okay, the point F on DC is such that DF is equals to DC itself. Okay, this in other words means that DF divided by DC equals to 1/4, or we can see it in ratio form. DF to DC has a ratio of 1:4. Okay. Understanding this into its various form is very helpful, okay, because very often we need to know some proportion. So DF being 1 unit, the entire thing is 4 units. That means that this is 1 unit and this will have to be 3 units. Okay, I'm looking at things in units itself, or I'm not looking at its exact value. Okay, so we're looking at proportion. Then in part IA, we want to express the following terms in terms of A and B. So AC, okay, will be this diagonal going past your parallelogram. So we know that AC can be expressed as AB plus BC. But this is not the only way that you can express it. You can also see it as though it is AD plus DC. But whichever way, we know that AB has the same vector as AD and BC has the same vector as DC because it is a side of a parallelogram. So AB itself would be 8A and BC would be 4B. So we find that AC equals to 8A plus 4B. know that DF is equals to 1/4 of DC. Taking note that in our question, DF and DC, when they write it in this manner, okay, in this notation, this refers to magnitude or length. Okay, so this is an alternative way of writing. Okay, instead of writing it in this manner. Right, so for magnitude, either you write it in this way or else you can write it this way. Right? So for the vector DF itself, it is 1/4 of DC. We must ensure that when I write this expression in vector form, the direction is the same. So from DF, it is going forward and then DC is going forward as well. You cannot tell me that DF is equals to 1/4 of CD. Okay? Because it is not all the time that the question, okay, when they give it to you in this manner, it is in the same direction. So you might need to do some adjustment in terms of direction on your own. Okay. So DC, we know that it is a side on the parallelogram, which is the same as AB. So therefore, that is 8A. And hence we see that DF is equals to 2A. Okay. Then looking at CF, right? Okay. CF is in the opposite direction of your DC or DF. Okay, so CF, just now, based on the given information, I already recognize that this is 3 units. 3 units out of the entire length of 4 units. So CF is 3/4 of your vector CD. Okay, we must ensure same direction. CF is now going in this direction. CD is also in that direction. Okay, and CD is the opposite of AB, so it's negative 8A. And 3/4 times negative 8 will give us negative 6. So part C, okay, will have the vector negative 6A. I will save part D and part 2 for tomorrow because part D will require some understanding of similar triangles. Okay, so when it comes to our vector question, it does rely on our similar triangles information. Right? So part D and part 2 I'll do it tomorrow, and then also the rest of the questions. Okay. No, tomorrow is your WA. I'm talking about Wednesday. Thursday. Sorry, today is Tuesday.